Welcome to the exploration of bridging data analytics paradigms, where we delve into the connections between frequentist statistics and data science, machine learning. The evolution of data analysis has witnessed the emergence of two seemingly distinct paradigms: classical frequentist statistics and modern machine learning. These approaches are often portrayed as fundamentally different in their philosophical foundations and methodological emphasis. Specifically, the former focuses on inference and parameter estimation while the latter emphasizes prediction and pattern recognition. Nevertheless, a deeper examination reveals several profound connections that demonstrate their shared mathematical heritage and complementary nature. Understanding these connections not only illuminates the theoretical underpinnings of both fields but also provides insights into how statistical principles continue to inform contemporary data science practices. At the most fundamental level, both frequentist statistics and machine learning share the core principle of extracting knowledge from observed data, based on the idea of maximum likelihood. Frequentist statistics conceptualizes this through sampling distributions and the behavior of estimators across repeated samples, while machine learning frames it through generalization error and the performance of learned models on new data. Despite different terminologies and emphases, both are grappling with the same fundamental challenge of making reliable inferences in the presence of uncertainty. While maximum likelihood estimation is a common thread, it is worth noting that Bayesian methods also occupy a significant role in both traditional statistics and modern machine learning. Techniques like Bayesian inference, variational methods, and Bayesian neural networks represent another deep bridge between paradigms, integrating uncertainty quantification directly into model estimation and prediction. Optimization as the common mathematical language. The connection through maximum likelihood estimation represents just the tip of this conceptual iceberg. Perhaps the most direct mathematical connection between frequentist statistics and machine learning lies in their shared reliance on optimization theory. Classical statistical estimation problems are fundamentally optimization problems, where we seek parameter values that minimize some loss function or maximize some objective function. Ordinary least squares regression minimizes the sum of squared residuals, maximum likelihood estimation maximizes the likelihood function, and robust estimation techniques minimize various loss functions designed to handle outliers. Machine learning has made this optimization perspective explicit and central to its methodology. Neural networks are trained by minimizing loss functions through gradient descent, support vector machines solve constrained optimization problems, and ensemble methods optimize weighted combinations of base learners. The mathematical machinery is remarkably similar. Both paradigms use calculus-based optimization techniques, deal with issues of local versus global optima, and employ iterative algorithms to find solutions. This connection runs deeper than mere mathematical convenience. The choice of loss function in both paradigms reflects assumptions about the underlying data-generating process and the relative costs of different types of errors. The squared error loss common in both regression analysis and neural network training embodies assumptions about Gaussian noise and symmetric error costs. The absolute error loss used in robust statistics and certain machine learning applications reflects different assumptions about outliers and error distributions. Regularization. From statistical bias variance to machine learning generalization. The concept of regularization provides another crucial bridge between the two paradigms, though it emerged from different motivations in each field. In classical statistics, ridge regression was developed in the 1970s to address the problem of multicollinearity in linear regression. When predictor variables are highly correlated, ordinary least squares estimates become unstable and exhibit high variance. Ridge regression introduces a penalty term that trades off some bias for a substantial reduction in variance, leading to more stable and often more accurate predictions. This statistical insight about the bias-variance trade-off became central to machine learning, where it was reframed as a tool for controlling overfitting. L2 regularization in neural networks serves the same mathematical function as ridge regression, penalizing large parameter values to prevent the model from fitting too closely to the training data. Similarly, the lasso, least absolute shrinkage and selection operator, developed in statistics for variable selection, became a cornerstone of sparse learning in machine learning, where it's valued for its ability to automatically select relevant features. The regularization connection illustrates how concepts can migrate between paradigms while serving different philosophical purposes. Statistics emphasized the inferential benefits of regularization, obtaining more reliable parameter estimates and better understanding of which variables matter. Machine learning emphasized the predictive benefits, achieving better generalization performance on new data. Yet the underlying mathematical principle remains the same: controlled shrinkage of parameter estimates can improve overall model performance. In fact, the development of the elastic net further bridges this conceptual space. Introduced as a hybrid of ridge and lasso regression, the elastic net combines the L2 penalty of ridge with the L1 penalty of lasso. This approach balances variable selection with coefficient shrinkage, addressing some limitations of each method individually. Elastic net is particularly effective in high-dimensional settings where variables are correlated and where model interpretability and generalization are both crucial. This model exemplifies how statistical innovations continue to evolve and integrate ideas across paradigms. Asymptotic theory and generalization. Different languages, similar concepts. Both paradigms grapple with fundamental questions about what happens as the amount of available data increases, though they approach these questions through different theoretical frameworks. Frequentist statistics has developed a rich asymptotic theory that studies the behavior of estimators as sample size approaches infinity. Concepts like consistency, estimators converge to true parameter values, asymptotic normality, sampling distributions approach normal distributions, and efficiency, achieving the lowest possible variance among unbiased estimators, provide theoretical guarantees about statistical procedures. Machine learning has developed parallel theoretical frameworks focused on generalization, the ability of learned models to perform well on new, unseen data. Statistical learning theory employs concepts like uniform convergence, Rademacher complexity, and PAC, probably approximately correct, learning bounds to provide theoretical guarantees about when and why machine learning algorithms can be expected to generalize successfully. These frameworks ask fundamentally similar questions. Under what conditions can we expect our procedures to work well? How does performance improve with more data? What are the fundamental limits of what we can learn? The mathematical techniques used in both asymptotic theory and generalization theory often overlap significantly. Both rely heavily on concentration inequalities, uniform laws of large numbers, and empirical process theory. The difference lies primarily in emphasis. Statistical asymptotic theory focuses on the properties of parameter estimates, while generalization theory focuses on prediction accuracy, but the underlying mathematical machinery is remarkably similar. Cross-validation, a statistical innovation adopted by machine learning. Cross-validation represents a particularly clear example of how methodological innovations can bridge paradigms. Originally developed in statistics during the 1960s and 1970s as a method for model selection and assessment under the resampling framework, cross-validation addressed the fundamental problem of how to estimate a model's performance on new data when you only have the data used to fit the model. The statistical insight was that by systematically holding out portions of the data during model fitting, one could obtain nearly unbiased estimates of out-of-sample performance. Machine learning adopted cross-validation wholesale, making it the gold standard for hyperparameter tuning, model selection, and performance evaluation. The k-fold cross-validation procedure used to select the regularization parameter in ridge regression is mathematically identical to the k-fold cross-validation used to select network architecture in deep learning. Both applications rely on the same statistical principle, using data splitting to simulate the process of prediction on new data. Despite their different emphases, the success of cross-validation in both paradigms highlights their shared concern with generalizability. Whether called external validity in statistics or generalization performance in machine learning, both fields recognize that models must perform well beyond the specific dataset used for their development. Cross-validation provides a principled way to estimate this crucial quantity without requiring additional data collection. Ensemble methods. Statistical bootstrap meets machine learning. The development of ensemble methods provides another compelling example of cross-paradigm fertilization. Bootstrap aggregating, or bagging, emerged directly from the statistical bootstrap procedure developed by Bradley Efron in the late 1970s. The bootstrap was originally conceived as a computer-intensive method for generating the empirical sampling distribution of statistics without making distributional assumptions. By repeatedly resampling from the original dataset with replacement, the bootstrap creates multiple bootstrap samples that mimic the variability that would be observed across different samples from the population. Leo Breiman's insight in the 1990s was to apply this resampling idea to prediction problems. Instead of using bootstrap samples to estimate the variability of a single statistic, bagging uses bootstrap samples to create multiple versions of a prediction model, then averages their predictions. This approach leverages the statistical principle that averaging multiple independent estimates typically reduces variance without introducing bias. Random forests extended this idea by adding randomness in feature selection. Information theory, the mathematical bridge. Information theoretic concepts provide another crucial connection between frequentist statistics and machine learning, particularly in model selection and complexity control. The Akaika Information Criterion, AIC, developed in the 1970s, was one of the first systematic approaches to avoid model complexity. AIC estimates the expected out-of-sample log likelihood of a model, penalizing models with more parameters to account for their greater flexibility and potential for overfitting. This information theoretic approach to model selection has become central to machine learning, where it appears in various forms such as the Bayesian Information Criterion, BIC, minimum description length, MDL, principles, and modern regularization techniques. The underlying insight, that model complexity should be penalized to avoid overfitting, is shared between both paradigms, though the specific implementations may differ. Information theory also provides the mathematical foundation for understanding concepts like mutual information, entropy, and divergence measures that appear in both statistical inference and machine learning. These concepts help formalize notions of similarity, independence, and information content that are crucial for understanding when and why both statistical and machine learning methods work. Moreover, commonly used loss functions such as cross-entropy in classification tasks are directly grounded in information theoretic principles, further solidifying the conceptual bridge. Computational statistics, the methodological convergence. The computational revolution has created another important bridge between frequentist statistics and machine learning. As datasets have grown larger and models more complex, both fields have increasingly relied on similar computational techniques. Monte Carlo methods, originally developed for statistical simulation, are now central to many machine learning algorithms. Markov chain Monte Carlo, MCMC, techniques used for Bayesian inference share computational strategies with certain machine learning optimization algorithms. Similarly, the expectation maximization algorithm, developed in statistics for maximum likelihood estimation with missing data, has found widespread application in machine learning for clustering, dimensionality reduction, and latent variable modeling. The computational challenges of optimization in high-dimensional spaces are shared by both paradigms, leading to the adoption of similar algorithmic solutions. In conclusion, these fields are deeply interconnected. The connections between frequentist statistics and modern machine learning run much deeper than their shared use of maximum likelihood estimation. From optimization theory and regularization to asymptotic theory and ensemble methods, these paradigms share fundamental mathematical principles and methodological approaches. Understanding these connections is crucial for practitioners who wish to leverage the best insights from both traditions. Rather than viewing frequentist statistics and machine learning as competing paradigms, it's more productive to see them as complementary approaches to the common goal of extracting knowledge from data. The mathematical and methodological bridges between them suggest that the future of data science lies not in choosing one paradigm over another, but in thoughtfully integrating their respective strengths to address increasingly complex real-world problems. As data continues to grow in volume and complexity, The synthesis of statistical rigor and machine learning innovation will become increasingly important for advancing our ability to understand and predict the world around us. Do you think students should dive straight into data science and machine learning, or is it better to first build a solid foundation in classical statistics? Would that background give them a better edge in understanding DSML concepts more deeply? Also, what other connections or common ground do you see between traditional statistics and modern data science? I'd love to hear your thoughts. Drop a comment below. If you found this video helpful, don't forget to like, share, and subscribe. Thanks for watching. Mahalo.